and people, I think, will continue arriving. But I think for the purpose of time, we should start right on time. So good morning, good afternoon, and good evening. I am Nicola Seriani. I'm one of the organizers of this 20th edition of the Total Energy Workshop, together with Francesco Mauri from the Sapienza University of Rome and Tanusri Sahadasgupta from the Bose National Center for Basic Sciences in Kolkata. So I welcome you here, and I give the word to Tanusri, one of the other organizers, who will also say a few words before I leave the word to ICTP's director, Atish Dabholkar. So Tanusri, do you want to say?
Dear friends and colleagues from various parts of world, very good morning, good afternoon, good evening, whatever is appropriate. On behalf of Francesco Mauri, Nicola Sarini, and myself, Tanusri Sadas Gupta, warm welcome to 20th International Workshop on Computational Physics and Material Science, Total Energy and Force Methods, which will be held on online platform. As you know now, due to the present pandemic situation, the total energy meeting this time, it's unprecedented, but this is happening neither in Trieste as done traditionally, nor in the originally planned dates, but happening in slightly delayed dates, and also with the online micro version of the meeting. As you have also realized, it's not the full length of the meeting that we normally have. And this decision of online micro format was taken not so long ago. So we had to really work within a short time scale and on a new platform that has not been really tested before. Prior apologies to any difficulties that may cause due to this. As you have also noticed, this event will take place daily from 1:30 p.m. to 5:30 p.m. Central European time to allow participation from many different time zones across the world. And beside 3 plenary talks, there will be 12 contributed talks and 3 poster sessions. I request you to attend all the session, as we believe all of them will be exciting, covering a vast range, starting from method development to energy, magnetism, 2D materials, surfaces, nanoscale, atomic and molecular physics. With these few words, I would like to welcome all of you once again and looking forward to exciting presentations, simulating discussion in coming 3 days. Thank you very much.
Thank you, Tanusri. And I will now give the word. We also have the ICTP director here in recognition of the importance of this event. So let's welcome Atish Dabholkar. Thank you, Atish.
Okay, thank you, Nicola. It's a great pleasure for me to be I just want to say a few words. I think for an outsider like me, it's impressive how far this field has come in computational physics and material science, that we can really, design materials in this manner, on a computer. And ICTP has supported this scientific community for a long time, and it's great to see that it has evolved to have a workshop with, as I understand, 950 participants today. So that's quite impressive. And I'm also very happy to have very distinguished speakers today, Professor Parinello, Professor Spalding, and Professor Zunger. And some of them actually are known to ICTP for a long time. But for example, Michele is the Dirac medalist, and he has been a member of our scientific council for a long time. So welcome you all, and I wish you a very productive and interesting meeting. Thank you.
So thank you very much, Atish, for these nice words. But let's take also a couple of minutes to say who is hosting us, what is ICTP. So I will now briefly share my screen to show you where you are, at least virtually. So I hope you see my my slide. So this is where you are now. Virtually, this is the ICTP, so which was founded in 1964 by Nobel laureate Abdus Salam.
Sorry, Nicola, I cannot see.
Yeah. Everything is dark now.
Okay.
It showed for a while, but then it went dark.
Okay. Sharing. Okay. Yes, I think I should resume sharing.
Maybe you can stop sharing and start once again.
Yeah, maybe I will do that. Let's share the screen again. So do you see it now?
Yeah.
Okay.
The second page, you can start from the first page, yes.
Okay, yes. So you probably, okay, so sorry. So this is ICTP. So I hope now you see it all. So this is where you are, at least virtually. And this is a institute was founded in 1964 by Nobel laureates Abdus Salam to enhance international cooperation through science. So he experienced firsthand how difficult it was to do science in some countries, and he wanted to overcome that through an international institute that would support scientists everywhere in the world. And therefore, this institute now combines the two tasks of performing high research at high level with the task of building scientific capacity in the developing world. And it's administratively part of UNESCO and is governed by an agreement between Italy, UNESCO, and the International Atomic Energy Agency. So we are active in research, education, and outreach. And we have a vibrant program of exchanges and conferences and visits, now virtual mostly, but not completely. But we really welcome scientists from all over the world. So in this spirit, I stop now sharing. We are now organizing this conference. Of course, it's not the usual full format, but we decided that it was needed to keep this community together. And we decided, therefore, to change a bit also the structure to allow for contributed talks, which is unusual for this kind of workshop. So also given the unusual format and conditions, we have other changes. So usually the Total Energy Workshop is the place where the Walter Kohn Prize is announced and given. But this year we have I have an announcement to make regarding the Walter Kohn Prize for Quantum Mechanical Materials Modeling, jointly instituted and co-funded by ICTP and the Quantum Espresso Foundation. So the prize is normally awarded biennially on the occasion of this workshop to a young scientist for outstanding contribution in the field of quantum mechanical materials and molecular modeling, performed in a developing country or emerging economy, with emphasis on first principle techniques. However, this year, ICTP and the Quantum Espresso Foundation have decided that, considering the short and virtual character of this year's total energy, the prize will not be awarded in 2021. So ICTP and the Quantum Espresso Foundation look forward to award the next Walter Kohn Prize at the next Total Energy Conference in 2023, so in 2 years. Nominations already submitted for this year will be automatically considered also for 2023, together with any nomination that will be submitted on the occasion of the new call for nominations, which will be announced in spring 2022. So this is an important communication, so don't worry, you will still be considered in 2 years. So now let's turn to some practical issues. So we'll soon start the first plenary talk by Alex Zunger, and I will soon give the word to Emilio Artacho. So as you see, some of you have already tried to use the question and answer session option, so which will be one way to ask question, or alternatively, or in addition, you can also raise your hand. So depending on time, we will either give you voice or we'll read your written question. We will see a bit how it goes. when you ask a question, especially by voice, we invite you to say your name and affiliation. So it will be a way to make the thing a bit more interactive. And the second thing, I hope you have received all the instructions how to connect for the poster sessions. We are looking forward. This will be also very interactive with many rooms. So I hope you have all the instructions. And with this, I welcome you to this workshop, which we are going to start. So I say thank you again to Professor Atish Dabholkar for coming to the opening session, and I give the word to the chair of the first plenary session, to Emilio Artacho, who will now take over from me. So thank you very much.
Hello, good afternoon, good morning. It is really a pleasure for me to be starting with the first plenary session, and it's really an honor to be introducing Professor Alex Sunga. He is really a pioneer of this community. He was there when the very first calculations of total energy and forces were done, when he was putting together with Marvin Cohen and others, the first calculations of the kind we all do and love. So it's really great to start this conference with his talk. And let me just give him the opportunity to talk himself. He's going to tell us about the essential physics needed to understand the basic electronic properties of 3D oxides. So Alex.
Thank you very much, Emilio. And good afternoon, everybody. And thank you for logging in for this meeting. Before I talk about the subject today, I wanted to say a few words about the subject of the meeting, since it is the 20th issue of this meeting of total energy. And it so happened that I recently found out the referee report of the very first paper on total energy and forces that we did. And I was going to show you the referee report so you can have a good perspective of what happened and how much people did not like this field 40 years ago. So everybody probably knows that the problem with total energy was traditionally that for a periodic system, each term in the total energy diverges. And by the 70s, there was no expression that included, I assume everybody can see my cursor, correct?
Yes.
Yeah. So there was the problem that the different terms were diverging, and there was no expression for that. But at the same time, everybody wanted total energy because the chemist had total energy for molecules, and we wanted to have that for periodic solids, except that it was difficult to find. So some of the first steps of early total energy was specialized to spherical potentials like muffin-tin or cellular methods. And in this case, the calculation reduced to one-dimensional integrals. And the problem of divergency of electron-electron, electron-ion was not, it was very easy to handle. So in those days, the theory was applied basically to electronically closed shell elements and closed spec structures for which spherical densities and spherical potentials were considered reasonable. And this work was before my time, was Frank Averill, Snow, who did copper, Janak, who did alkali metals and rare earth solids, Jack Sabin, who did neon with the one-dimensional integrals, and then Janak and Williams did the alkali metals and so on. The point is that at this stage in the mid-70s, it became clear that we are interested not only in shell and highly packed metals, but also in open structures like semiconductors, insulators, oxides, and so on. So actually my first postdoc with Art Freeman was developing the first closed form for total energy in 3 dimensions without any shape approximation. And this was applied to lithium fluoride, diamond, boron nitride, and so on in the 1976, 77. And we remember the first result of total energy in those days, it was all electron LCO. And for the first time, we saw that actually, while the total energy was very good in terms of lattice constant and the bulk modulus and so on, at the same time, the same method gave very bad band gaps and very bad transitions. In fact, the band gap of diamond was about half of what it is experimentally. I remember Art Freeman was very concerned that we will publish a paper on density functional showing that the band gaps are about 50% wrong, even though the total energy is very good in terms of ground state properties. But in any event, I convinced him that I should put a section in this early paper on self-interaction correction that explained in part why the band gaps were wrong, so he let me publish that. We then, when I moved to Berkeley in 77, I guess, there was really the main idea to extend this kind of thinking to plane waves. And I was fortunate to find there Jisoo Nim, who was a graduate student. And there we developed a closed form, again, 3D, without any shape approximation. That's the momentum space approach. It was applied very soon by Jisoo to silicon and silicon surfaces, and then by me to molybdenum and tungsten solids. And we looked at lattice constants, pressure, and so on. And this, to some extent, can be viewed as the beginning of the modern era of first principles, in the sense that it became possible in coming years look at structures, charge densities, phonons, pressures, and so on and so forth. And the paper, actually, many people asked me, why did you publish the paper in the British journal, so Journal of Physics C, and not in the journals that were then more contemporary in the United States, at least, like PhysRev? And the answer is because the paper was rejected. It was rejected by PhysRev. Here is the referee report of the very first paper, was submitted in December 78. That's a paper on the momentum space, plane wave forces. And the referee said, journal space is really too valuable to devote an entire paper to routine algebraic manipulations of direct interest to only few computational scientists. And he kept saying, I am inclined, with a British accent, I'm sure, to be firm on this recommendation. Anyhow, in the last 40 years, we tried to figure out who the person is. I think we know. But in any event, I want to say to all of the students and the postdocs that if you get your papers rejected, really, it's very normal. Even the papers that eventually were successful were rejected, not because of correctness or incorrectness, but because 40 years ago, the perspective was that getting the right expression for computational solid-state physics wasn't an important thing. So with this, let me move on to what I wanted to talk today about, and this is the application of this ideology to oxides of 3D oxides. My collaborators are Giancarlo Trimarchi, Julien Varignon, Ji Wang, Shihan Lu, and Sasha Malay, and the work was done at the University of Colorado. So those oxides, as many of you know, have a very broad range of properties. There is the low temperature phases, which are usually ordered magnetically, and there is the high temperature phases. You can have different d electron counts from yttrium, titanium, lanthanum, manganese, and so on. The structures can be orthorhombic, cubic, monoclinic. The spin order at low temperature can be very diverse, antiferromagnetic, spiral, ferromagnetic, and mostly they are insulators at a low temperature. And then at high temperature, there is spin disorder, and you get the paramagnetic phase with all kinds of similar properties, except some insulators can become metals. So this is a very, very rich group of materials. The interesting effects are orbital ordering, mass enhancement, disproportionation, gapping in systems that have an odd number of electrons, not expected to have a gap, and so on. The cousin of the oxide perovskite are halide perovskite, like cesium tin iodide. And I would like to include them as a group because they have the same structure, similar phenomenology, except they do not have d electrons and therefore cannot be blamed of being correlated. Nevertheless, it's a good point to measure everything else relative to that. Issue number one, the traditional textbook view on gapping with an odd number of electrons. So when you look at all of those oxides, starting from the days of Mott and later Hubbard, at low temperature, they're antiferromagnetic, and they're insulating, most of them. And everybody says, of course, they're insulating because there is long-range order. The spin are ordered, and there is cell doubling. But then at higher temperature, there are paramagnetics. And the question is, why would a paramagnet still be an insulator, given that it does not have long-range order? Everybody expected them to have zero gap. But experimentally, as I just showed, they had band gaps of 2, 3, 4, 5 eV. So it was not a simple mistake, it was a huge mistake. This was discovered already in the 1950s, and this conflict between band theory and experiment was really the main driving force for the development of highly correlated methods that were based on the ratio between the interelectronic repulsion and the bandwidth. I mentioned in passing that the paramagnetic phase that was considered in those days was actually interpreted not only to have zero magnetic moment, but that each atom has a zero magnetic moment. And this was a special feature in terms of how this thing was viewed. Here is a modern example of, say, cobalt oxide band structure. If you calculate the paramagnetic phase in the same style they did in those days, you see that the Fermi level cuts through a band and it's a metal. Everybody knows that cobalt oxide is a wide gap insulator. So this is the example of the conflict that started lots of questions. What did the literature, if you look back at the literature from 1960s, 70s, 80s, and 90s, what is the impression of the literature of this conflict that was really shocking according to the literature in those days? The impression, as you'll see, is that the correlation is everything that DFT does not get right. And the impression was that DFT fails for most 3D oxide and most properties of 3D oxides. Since then, I would say that there was a certain fashion that in the last 30 years to see correlation everywhere. It was the correlation-induced syndrome. To get papers published in many good journals, it was very helpful to say that there is correlation-induced orbital order, correlation-induced band competition, correlation-induced semiconductor gap, correlation-induced displacements, correlation-induced disproportionation. In short, more and more effects were rebaptized as correlation-induced. Le Figaro always, they're always right. So they said that the standard DFT and DFT plus U, I'm kidding, Le Figaro did not say that, I said that. But this is you find in the literature in PhysRev. They said DFT fails to describe the phase diagram, with DFT predicting that all compounds remain metallic and undisproportionated. These results establish that strong electronic correlation are crucial to structural phase transitions, and methods beyond DFT, like DFT plus U, are required to properly describe them. About nickel oxide, a very simple compound, they say that conventional band theory, which stress the localized nature of electrons, cannot explain the large gap predicted in nickel oxide. For this reason, nickel oxide has long been viewed as a prototype MOT insulator. L'Osservatore Romano, I'm sure they also had a strong dogma on that. If you look at the lanthanum cap rate, people in PhysRev actually said, while density functional band theory is the workhorse of material science, it does not capture the physics of MOT charge transfer insulator transitions, or that these methods, LDA, GGA, and so on, usually fail to describe correct electronic structure of electronically correlated paramagnetic materials, and so on and so forth. Well, Pravda said that the properties of all of these practical things like catalysis, ion batteries, ferroelectrics, and so on, which are very often transition metal oxides, cannot be trusted if you calculate them by density functional. The functional that failed is the N density functional method, where N means naive. So the naive density functional approach uses the view that each unit cell has a single motif, for instance, an octahedron or tetrahedron, and use the smallest possible number of highest symmetry unit cells, single motifs, to calculate the electronic structure. There are three kinds of systems that we are talking about. Systems where the atomic positions are not ideal. These are positionally monomorphous, for instance, paraelastics, or a case where the spin degree of freedom is not a simple spin up, spin down, but maybe local arrangements of spin. And then there is a dipole monomorphous, systems that are paraelectric. So for those three classes where the para phase can have some kind of order, the opinion in the literature was you cannot use mean field theory such as density functional. What I'd like to show you today is the results of our work from the last 2 years, again, using total energy. And we'd like to show that the naive density functional assumptions indicated here, these assumptions led to the failure of the approach rather than lack of correlation. So assuming the simple naive DFT created many predictions of metallic state in systems that are not metals. And further, I'd like to indicate that there is no need to leapfrog, to jump from naive DFT to dynamically correlated methods and skipping DFT. There is a possibility to check what DFT, uncomplicated by naive approximations, what DFT would say. Of course, it's not perfect, but let's find out what DFT says, given that the initial accusation of DFT was based on something that is not really DFT. It's a naive form of DFT, which I would explain. At this point, maybe it makes sense to mention that when you choose a unit cell and when you calculate band structure, the size of the unit cell to some extent is your choice. Most of us try to use the smallest possible unit cell. But basically, you can see that if you look at the crystallographic literature for halide perovskite or oxide perovskite, very often they take the unit cell of the cubic structure, where there is a simple octahedra, no tilting, no motion, everything looks as an ideal structure. And this is the crystallographic picture, which of course takes an average over a large coherence length. Now, there are two kinds of, so let me say, for instance, let's say you take this cubic material, which is famodium tin iodide, it's perovskite. You can make a supercell where each unit cell is identified. And if you do that and you check what is the tilting angles of the octahedra, in the simple case of no relaxation, you find a single tilting angle of 0 degrees. If you look at the displacement of the B side, you find a single value, 0. And if you look at the octahedral volume, you find a single value. On the other hand, if you take this supercell and keep the outer cubic shape, and you allow the atoms inside the cubic shape to relax, you find a distribution shown in red of tilting angles between 0 and maybe 10 degrees. You find a distribution of B atom displacements, and you find a distribution of volumes. And if you check the total energy, here I show the reduction in total energy due to this relaxation. So obviously, these kinds of systems are not, even in the static picture, before you put temperature and molecular dynamics, already they don't have the simple structure that was envisioned in the 1950s, 60s, 70s, and 80s. What about spin? If you take, for instance, iron selenide at the tetragonal phase, in the paramagnetic phase, you can imagine, like in the old days, that it had a single magnetic moment and it was 0 because it's a paramagnet here. On the other hand, if you make a supercell of iron selenide in the correct structure, but you let the local magnetic moment be a variable, you find that the total moment is 0, but it is 0 not because each moment is 0, it is 0 because the vector sum is 0. You find a distribution of moments that are negative, a distribution that is positive, and the sum is of course 0. Again, this is no longer the monomorphous view of a single motif, it's a polymorphous view that there is a distribution of motifs that of course has the right general subgroup. How about paraelectrics? You know, if you take paraelectric like barium titanate, in the cubic phase, cubic paraelectric, can you believe it's experimentally piezoelectric? Now, cubic cannot be piezoelectric. I mean, it has inversion symmetry. So what is happening? This is not a simple mistake that the shape of the sample was wrong or that there was a hole in the sample. But if you actually calculate the dipoles in barium titanate, in the supercell of barium titanate, for instance, 4 by 4 by 4, you keep the shape cubic, but you let the dipoles relax the minimum total energy, you find certain distribution of dipoles along 3 crystallographic directions. And guess what? This system is no longer centrosymmetric. After you do that, the paraelectric phase loses inversion symmetry, and it definitely can be piezoelectric. So let me try to summarize basically what was the point of divergence. The early mistake that the theoretical community did was to look at the average global structure taken from crystallography and to take this structure and use it as input to do band structure calculation, rather than consider the fact that the structure can have local motifs that are not captured by XRD, especially if you don't collect sufficient intensities. So the basic point is the following. Global symmetry equal local symmetry in cases where the repeat unit is the same. For instance, in gallium arsenide, if you calculate the total energy for a primitive cell or for 10 primitive cells, you get the same answer per cell. So that is where global equal local. However, in many oxide perovskite and halide perovskite, the global symmetry can be cubic, but the local symmetry can deviate from cubic. In this case, there is no sense of averaging the different configurations in the system. You cannot average a chicken and a horse. It's meaningless. The naive DFT approach of many, many years used the monomorphous point of view to describe a physical situation that is intrinsically polymorphous, meaning has a distribution of local motifs. Just to put it slightly formally, if you have a system that has many configurations, SI being a structural configuration, you can take the average configuration if you want to, call it S0. One way to calculate properties P, like moments or band structure, is to take the property of the average configuration, the property P of the average configuration. This, of course, is not correct. The correct way to handle an ensemble is to calculate the average of the properties of individual configurations. So this is the property of a given configuration SI, and the physical property of interest, like band structure or moments, is the property, the average of the property, not the property of the average structure. As simple as this sounds to you, this is the mistake that was made over and over and over again. Well, there is a simple common sense test to see what is happening. If you take all of those oxide with 3D elements in the paramagnetic phase, you can ask yourself, what is the difference in total energy between the naive approach that takes the average configuration and the actual total energy where the symmetry is broken? That is, you have different distribution. Here is the difference in total energy. This is in millivolts. So, for instance, the mistake you make is 1.9 EV, 1900 millivolts. It can be 4 EV, it can be 2 EV, it can be 3 EV. In short, if the naive DFT gives a physically irrelevant high energy metallic state because you take the wrong configuration. This was used, the fact that you always get a metallic state was used to suggest that dynamically correlated methods are really needed. Issue number 3. What do you have to do to get correct symmetry breaking when the system wants to break symmetry and lower the energy? Well, you have to do 3 things. First thing, if you talk about spin system, you have to acknowledge that the spin can be spin polymorphous. What do I mean? In an antiferromagnet, you can have a single spin configuration. Each spin up is surrounded by spin down, and each spin down by spin up. However, you should let the system a possibility to have a distribution of such configuration. Sometimes up is surrounded only by down. Sometimes spin up is surrounded by some up and some down. You should allow this as a possibility. To do that, you have to use a bigger unit cell. And how you can do that? One possibility is to treat the spin more, for instance, with a special quasi-random structure. If you do that, before you do that, cobalt oxide, I said, is naively a metal. But if you allow the spin to have a distribution, even the same crystal structure, the same everything, you have a band gap of 2.4 eV without any additional work, just allowing the spin to break symmetry. Many people wrote papers that yttrium titanate and lanthanum titanate are metals in DFT. Guess what? They are metals only if you take the average spin structure. You see the Fermi level is in the conduction band in yttrium titanate and lanthanum titanate. In reality, if you allow the spin to have a paramagnetic distribution, you have a very decent gap. The second thing you have to do in order to do it correctly is to take care of positional polymorphos. In other words, what if the system wants to adopt different local environments? There were a bunch of papers over the years saying that strontium bismuth oxide is a metal. Guess what? It's a metal only if you neglect the possibility that some octahedra would like to double and some octahedra would like to stay a single octahedra. You see, the band structure is a metallic state for when you have a single environment, but it has a gap if you allow the system to alternate between small and large octahedra, just positional relaxation. Lanthanum manganate, many people said it's a metal in DFT. Turns out it has a Young-Taylor distortion, everybody knows that. And if you don't put the distortion, you have a metal. And if you put the distortion, you have an insulator. So all of those things have to be taken care of. The third thing you have to take care of is to use an appropriate exchange correlation functional. Imagine if you use a functional that gives you very, very diffuse orbitals. If the orbitals are very broad, they cannot see local environment. So the functional has to have a certain amount of elimination of self-interaction correction. For instance, if you take lithium titanium oxide and you use a functional like PBE that gives very extended orbitals, the system is a metal. Okay. However, if you use a functional that has the ability to create some localized states, meaning orbitals that are not totally diffuse, you find that the system is an insulator. And of course, you find some titanium atoms that can be characterized as titanium 4+, other titanium 3+. In other words, there is a natural distribution of local environments. And you have to do all of those three things to get that right. Let me go over some of the interesting results and of what happens when you allow symmetry breaking in density functional, doing three things: spin symmetry breaking if it wants to do that, positional symmetry breaking, and dipolar symmetry breaking. In each system, it's a different symmetry breaking. The point is that symmetry breaking in density functional, as you'll see, surprisingly explains effects that used to be exclusively explained by highly correlated methods. Mean field density functional with symmetry breaking can explain effects that we all thought are exclusively highly correlated effects. Not all, but many of them. So let me give you a few examples. Result number one, general trends. This table is not meant to look in great detail, but here is the reference where you can find the table and you can zoom into different aspects of the table. It shows you for all of those 3D oxide indicated here, for low temperature phase and high temperature phase. It shows you what magnetic state it has for ordered and disordered, what crystal structure it has, whether it opens gap or not. And every time you see a green check mark, it means that DFT with a large supercell allowing symmetry breaking actually gets the right answer. Result number two, providing chemical and physical insight about what causes that. You know, if you do the classical Mott-Hubbard theory, there is one universal reason, one size fits all, why you open a gap. And this is when U is larger than W. However, if you do supercell with symmetry breaking, you find many, many different reasons. You find that calcium manganate and lanthanum iron oxide, the reason they have a gap is because the subshells in this system are actually a half filled, exactly half filled. However, if you look at other compounds like yttrium titanate and lanthanum manganate, if you analyze the DFT results, you see that the lifting of electronic degeneracies happens due to octahedral rotation. However, if you look at two other compounds, calcium vanadate and strontium vanadate, you see that the octahedral rotation is quantitatively so small that it is not enough to open a gap, and therefore these systems are indeed metals. Mechanism 3 is lanthanum vanadate, where you have 2 electrons in the T shell, and the reason DFT opens a gap here is primarily due to orbital broken symmetry. Those 2 electrons are not positions 2/3 of an electron in each of the 3 degenerate partners, but you have occupation of 1 electron, and 0 electron. So this is occupational broken symmetry, and you can do that with DFT. Finally, mechanism 4 is that calcium iron oxide and these compounds actually can have a gap because of disproportionation, that some octahedra are small and some octahedra are large, and this is a 3-dimensional analog of the Peierls instability. It opens a gap. Result number 3. Must we have U? If you like it, you can have it. But you can do the calculation of those ternary compounds. By setting U equals 0, you need to have a little bit better functional. So this is the scan functional. And these are the density of states of different compounds indicated here. And the dashed line are indicating the VBM and the CBM. And you see all of them have gaps as they should have, even where U equals 0. So you don't really have to put U to see any gap there. But many people like to put DFT plus U. Do that in good health. If you like it, no problem. But it's not a necessity. Result number 4, structural symmetry breaking. Those octahedra in cubic compounds and other compounds can have tilting and different modes indicated usually by this notation of Glaser, but these are allowed modes. In the old days, about 7 years ago, papers were written that in order to get a Young-Taylor distortion in lanthanum manganate, you really have to have a correlated method like DMFT. And if you use the regular DFT, then there is no relaxation in the system. Well, of course, the DFT used in those days was non-magnetic DFT, and of course, this means nothing. But if you do DFT allowing the system to have Young-Taylor distortion and have a spin order, you can find that, in DFT, there is, of course, energy lowering due to those distortions, and the energy lowering is very reasonable. And you can compare the experimental distortion to those computed by DFT with symmetry breaking, and basically the chemical trends are correct. Result number 4, mass enhancement. Mass enhancement is an effect that is sort of a curious effect, and this is if you actually measure the effective mass of electrons or holes in a bunch of materials, you see that in some materials, which I will illustrate now, the effective mass of electrons or holes is bigger than the effective mass as obtained by simple textbook DFT. The ratio between them is 1.2, 1.3, 1.5, even 2, and it's called mass enhancement. And it's subject that many people in the high TC field and other fields of correlated materials were very occupied by. What really causes mass enhancement? I have to make a small comment, and this is, if you want to calculate those quantities, you have to be aware of the fact that if you do a big supercell of typically 200 or 300 atoms, of course, you get very complicated band structure. You get a spaghetti-looking band structure, and therefore, many people were discouraged by supercells, but in fact, you can do an effective band structure where you unfold this band structure into the primitive Brillouin zone. And if you do that, you get a band structure, a normal DFT. It has a coherent part and incoherent part, but bands are not infinitely sharp. They have some kind of fuzziness. Okay, so this is the effective band structure. So the effective mass you get is the effective mass. It's the effective mass obtained from downfolding the big unit cell, because the big supercell can have relaxation, can have spin arrangement, can have short range order. All of these will be folded into the primitive Brillouin zone, and you get an effective mass that includes all of those mean field effects. So if you take strontium vanadate, if you calculate the band structure of this compound in naive DFT, you see the conduction band is relatively very, very broad, and the width of the conduction band is 2.6 CV, and experimentally it's only half of that. And everybody said, oh, this is a tragedy. DFT is really terrible because the band is too wide and there is no mass enhancement. But if you take strontium vanadate and you do it in a large supercell, you keep the structure cubic, you keep the lattice constant, everything okay, but you relax the spins and allow them to create local environment in the paramagnetic phase. And then you do unfolding. Here is what you get. The width of the conduction band went down to 1.6 CV, just because of local spin arrangements. It's a paramagnet, but now it's instead of being 2.6 to 1.6 CV. DMFT with a lot of work gets a bandwidth of 1.2 eV. In short, you can, instead of doing GW plus DMFT, you can do straight DFT, and you already capture 80–90% of the mass enhancement. Even if you take a compound like cesium lead iodide, which does not have any suspicion of correlation, no d electrons, no open shells, if you calculate this band structure without making a big unit cell, the ratio, the mass enhancement is 1, meaning no enhancement for electrons and holes. But if you do a big unit cell, keep the shape constant, cubic in this case, and relax the octahedra, allow them to rotate, then calculate the band structure, you have a mass enhancement of 70% or 100%. So this is the mass enhancement you get for mean field effects. Result number 6, I think that's the last one, maybe. How about, can we measure the local environment that I'm talking about? Can we measure the local environment? Well, there is a method called pair distribution function, and it measures the distance between atoms in a short range distance, say up to, say, 7 angstrom, but you can also go up to, say, 20 or 30 angstrom. If you take the compound, so this is, for instance, a cubic perovskite. The black line here is the experimental PDF. The red line is the PDF calculated from density functional using a large supercell that includes all of those relaxations. The green line is the difference between experiment and theory. And it's not fantastic, but it's pretty good. Why pretty good? Because if you use the primitive unit cell taken from X-ray, the error between experiment and theory is tragically large. So you can actually see those local environments experimentally. It's not a figment of my imagination. If you take a magnetic material, a superconductor like iron selenide, here the experimental PDF is shown in the blue line for short range and for long range. If you calculate that with a simple primitive unit cell, the difference between experiment and theory, shown in green, is huge. But if you allow spin to adopt local environments, as well as iron to adopt local environments, the difference between experiment and theory, shown in the green line, is very small here. So this is density functional, giving you the local environment, which X-ray did not see. X-ray missed that. Pair distribution function saw that. Well, I mentioned that we can do all of the calculation I mentioned so far are static energy relaxation, where you do with large supercell. But you can take these static things and actually start the molecular dynamics, where you look at the free energy in those compounds. And if you do that, here is what you get. For instance, calcium titanate. The blue results are the local displacements obtained from static total energy relaxation. And these are basically intrinsic displacements, not thermally induced. They are a reflection of the will of the chemical bonding. If you heat it up to 2000 degrees, shown here in this brown color, you find a distribution of the same kind of distribution, but the distribution is of course much wider. So what you see, the minimum of the internal energy U and the minimum of the free energy are related, because the internal energy gives you already the fingerprint of what the system are going to do when you make it a bigger one. So in a conclusion, let me say, now that we know that all of those transition metal oxides have a band gap, and you don't need special effects to get all of those things. You can get relaxation, you can get Young-Taylor effect, you can get disproportionation, and so on. This opens the possibility to actually do legitimate doping calculation for all of those correlated materials. And just to show you one type of doping calculation that surprised everybody, we are all used that when you dope a material by electrons, the Fermi level should move towards the conduction band. And when you dope it by holes, the Fermi level should move towards the valence band. Guess what? If you take yttrium nickelate and you look at its band structure, you see that the first empty band is actually a very special band because it has in it trapped holes. If you look at the charge density of this open band, you see that it has holes on those atoms, on the nickel atoms. If you dope the system by electrons, the electron goes into the empty band, it sees here a trapped hole, it recombines with it, and then this band starts moving towards the valence band. You doped with the electron n-type, and the Fermi level moves to the valence band. So this is electron anti-doping. And the same thing happens if you have a natural band that actually has trapped electrons, like the titanium. You dope it with holes, the Fermi level is going to move to the conduction band. So these are just examples of really unusual things that you find when dope quantum materials in this system. So let me conclude here and tell you where we are in this journey that we started about 2 years ago. Of course, there are many, many more things that we have to learn about. What we learn is that naive density functional that was practiced for many, many years, mostly by people who promoted highly correlated methods, that naive density functional tried to use a simple monomorphous picture, meaning a single structural motif, to describe a situation that is inherently inhomogeneous, polymorphous. The failure of naive DFT is not the failure of DFT itself. Symmetry breaking, and this is a very deep conclusion, symmetry breaking in mean field theory, spin or positional or dipolar, captures effects that in symmetry unbroken theory would require complex correlation effects. And that's very interesting. If you use a small supercell, small unit cell, and you have the electrons interacting strongly in a very small space with only one nickel atom or one manganese atom, you need very complicated rendering of electron-electron correlation to get it right. But if you spread the system by making replicas of the system and have spatial inhomogeneity, then you find that what used to be strong correlation is becoming actually weak correlation inside the DFT. And that's the reason, that's my current view why actually it works, having broken symmetry DFT. Finally, 3D oxides, I would say, are complicated, but not necessarily correlated. But complicated is good enough. Thank you very much.
Well, thank you very much. So we are running a little bit late, and I see already several questions. So there are at least 7, but I'm afraid we don't have the time for all of them. By the way, can you hear me? Probably yes. Yeah. And so let me just start with a question by Tanusri, if you could. Let me unmute.
Yes.
Yeah.
So the question I would like to ask is, one of the, the so-called failure of DFT and etc. that was kind of put up in the literature is like also a comparison with the photo emission data. Not only just the band gap opening, but there are these correlated metals where at least the photo emission do see appearance of some kind of a sub-band which was interpreted as presence of
sometimes what kind of band again?
So these sub-bands were some high energy sub-bands, and of course DFT didn't had any signature of such sub-bands.
Not high energy. No,
sorry?
Those bands were split of bands that were actually split about 1.5 eV down in energy.
Right.
For instance, strontium vanadate.
That's what I mean by high energy, because they were not really at the Fermi level. So in your disorder calculation or the inhomogeneous local environment, do you see signature of those high energy bands?
They are not high energy bands. So if you take systems, let me take an example here. So if you take systems that need to have some nudging in order to create impurity states, then you see those split of bands. We know that in physics of impurities, you usually have a state split from the conduction band going down by 1 or 2 eV due to impurity potential. However, think about it as electronic impurity, not really impurity. If you have a conduction band that looks very innocent, doesn't matter right now if it's a metal or not. However, if this conduction band has a localized particle in it, in this case, a localized hole, then if you actually let this localized hole minimize the energy, it would shift a state, which I show here, down by 1 eV or so into the band gap. And this effect can exist entirely in a mean field theory, and all of the cases of systems that have multiple oxidation state, like titanium, any nudging like that creates a deep impurity state, except the impurity is not a chemical impurity, it's an electronic impurity. And in my opinion, this is the reason why strontium vanadate and lithium titanate have those split of state of 1.5 eV shifted down from the Fermi level.
Okay, thank you.
Okay, there are many more questions, but I think we cannot go much further than this. Possibly, let me just take a first question that was raised by Nikitas Gitopoulos. Nikitas, can you speak? Can you unmute yourself or not? Possibly not. So I don't know how to make it from here. So let me just.
Okay. Well,
oh,
I think I can talk now.
Yes.
Thank you, Emilio. Thank you very much for your talk. My question is this, that in physics, we try to simplify the model as much as we can. That's why we have, this monomorphous, as you said, picture. It's in the effort.
We try to simplify, but it's better to be right than to be wrong.
Now, I know, exactly. That was the point of my question. We want to get the right answer, which is insulating behavior for the correct reason. So
and the Taylor effect, and disproportionation, and orbital order, all of these effects disappeared with the simplification.
Yeah, my question is this. Suppose that we can do a high-level theory like stochastic CI for solids, for example, Ali Alavi's work, or coupled cluster for solids, and we have this monomorphous picture with one unit cell, and we did a calculation. do you think that the DFT calculation would agree with the high-level theory, or does it not matter that at that level we do not have agreement, but in the real system, which is much more complicated, we might, restore the agreement, but it could be for the wrong reason?
Yeah, this is really a subject for discussion, but let me say the current view we have on that. If you look, for instance, at current results of a symmetry broken DFT and compare it with coupled cluster, for instance, even for molecules, okay, you see very surprisingly the following thing. In approximate implementation, a correlation that has been dynamic in the symmetry restricted view can become static in the symmetry broken view. You all know the cases from the 1970s where diatomic molecules, people were breaking the symmetry of diatomic molecules and got, by simple Hartree fork or unrestricted Hartree fork methods, got results that were much more similar to the highly correlated molecular calculation than people expected. The current view is that it is entirely possible that one form of correlation, dynamic correlation, that is obtained in small volumes can actually transform intrinsically into a weak correlation if you spread the total electron-electron interaction not on one atom, but on more atoms.
I understand. Thank you.
So I really think it's a matter of representation. You can represent the problem as dynamic, small volume symmetry unbroken, or represent it as static symmetry broken. In the exact implementation of both methods, the result should be the same by ergodicity. In the approximate implementation where we actually live, I think that the result should be very similar. And there are more and more cases where we find surprising successes of mean field relative to coupled cluster. However, the success is not surprising where you realize that the mean field actually broke many symmetries.
Okay, thank you. I fear we have to stop it here if I want to survive this session myself. And I thank very much.
All welcome to write to me questions. I'm happy to talk offline.
Yeah, you can. There will be opportunities to talk to Alex throughout the workshop. I know there I can see many more hands raised and many more questions there. Probably he can have a record of the questions that have been written in the question and answer, so he may be able to respond to that.
Give me the email also. That
offline. Yeah.
On the coffee break, you can fax me the coffee.
Yes. Okay, well, thank you very much. And I think I'll pass this on for the next. There is a pause now. There is a coffee break, I think, but I don't know whether we have already overrun. So,
let's take 2 minutes and start at 2:30. So 2 minutes just to stretch your legs, and then we start again with the next session with the contributed talks. So
okay. I thought you were going to fax the coffee, no?
Okay. Thanks. See you in a moment.
Thank you. So see you in a moment. We can use these 2 minutes. We can start.
Antimo, perhaps you can prepare your screen, your presentation.
Can you see it?
Yes.
Okay.
Oh.
Okay, so here in Trieste, it is 2:30 now, and Nicola has said we would continue after this very extended coffee break at 2:30. So hello, everyone. My name is Ralf Gebauer. I'm from ICTP, and I will chair this first contributed talk session here of this Total Energy Conference. I think we should start directly. So these 4 talks now are, each talk will be, say, 18 minutes, and then we foresee 3 minutes of questions. I don't know how many questions we will have time to deal with. I recommend everyone, if you have questions, type them in the Q&A on your screen, and then, well, we will see how many questions we will be able to ask. Okay, and to the speakers, I will give you a sign or interrupt you 5 minutes before the 18 minutes are over, just to give you an idea. Okay, so every talk is 18 minutes, 3 minutes of questions. And so our first speaker is Antimo Marazzo from the EPFL in Lausanne. And he will now talk about Kane-Meillet and emergent topology in Jequtingaite, whatever this is. Okay, so please go ahead, Antimo.
Thank you. And so let me start by just a big thank to everyone for being here today. Also to the organizer for inviting me here today to discuss about my work. So indeed, the title of my talk is Kane-Meillet, an emergent topology in Jequtingaite, or at least this, I think it's the right way to pronounce it, I hope. So I will discuss a lot about this specific material and its interesting physics and interesting properties. Especially, I will discuss a lot about it, the topology of its electronic structure, and I will discuss a lot about topological insulators. So I will start by introducing one type of topological insulators that is called quantum spin-on insulators. Essentially, they are 2-dimensional systems that are time reversal invariant, so they are not magnetic, and they are described by this Z2 topological invariant, which is essentially an integer, such that if you have a Z2 equal 0, you're just discussing a trivial insulator or a trivial semiconductor. If you have instead Z2 equal 1, you have this quantum spin-on insulator that are characterized by the presence of edge states that are localized here at the edges. And they essentially are helical states crossing the bulk band gap, and they are, to first approximation, made of opposite spins channels going to opposite directions, which you see here on the left-hand side picture. So these materials, they're very interesting for a number of reasons, but they also have interesting properties from an application point of view. So here are listed the 3 most relevant properties. They have low dissipation electron transport taking place at the 1-dimensional edges. These edge states are spin momentum locked, and also all this physics is somehow robust in the sense that it's protected by this non-trivial topology of the bulk electronic wave function. And people using this and other properties started since the very early days of the field to come up with different kinds of devices. What you see here is called topological field effect transistor, which is nothing but a switch, essentially. So you place your 2-dimensional system between electrical gates, and through an autoplane electric field, you switch off the topological phases. So you close the band gap and reopen the band gap in a trivial insulating phase, okay? And this was done by theorists just up to a few years ago. And now, these days, you start to see these ideas also arriving to the experimental laboratory. So this is what I show you here on the right-hand side is an example of a transition of this kind realized in experimental setup, essentially. So the field is progressing really fast. It's very exciting, but there is one major bottleneck, and that is that all this fundamental research and even potentially future technological applications are really hindered by the rarity of this material. So there are just a handful of systems where this effect has been observed, and in most cases, it doesn't survive room temperature, okay? So what we decided to do was to go for a computational screening for this material. So to try to find, with first principle simulations, novel candidates that could possibly outperform the state-of-the-art materials. And we decided to focus on exfoliable materials. So materials that you can think of peeling off, like you peel off graphene from graphite, MS2, hexagonal boron nitride, and alike. And this was actually a wider effort on 2D materials that was led by Nicolas Mounet at the PFL. We were essentially we found 1,800 materials that could be exfoliated by starting from more than 100,000 3-dimensional crystal structures. And this set of 1,800 materials, I look for quantum spin insulators. You see here, we compute a bunch of properties with dense functional theory and spin orbit coupling, band structures, the topological invariant, the Z2 invariant, phonons to assess stability. We also do some kind of refinement with many body perturbation theory. the G0 to 0 level. And at the end of this process, what we get is essentially a selected pool of candidates, and namely 13 candidates, which is what you see here. This is a plot of the band gap versus the average atomic number of the structure. You see that we found a number of candidates. Some of them were actually already known in the literature, but some of them were actually novel and they were proposed by us in this work. And in particular, we focus on this single material here, which is made of platinum, mercury, and selenium, and this is what is called jacutingate, and this is where I will spend the rest of my talk on. So jacutingate is actually a mineral. It's very interesting. It was discovered only basically 10 years ago by an expedition of geologists that went to Brazil to find noble minerals. They went to a Brazilian mine and they found jacutingate. They characterized it. It's a layer mineral made of, as I said, of mercury, platinum, selenium. It's cleavable, and we did essentially van der Waals, no-local van der Waals density function theory simulations, and we showed that you can actually potentially exfoliate this material into monolayers. Okay, and once you study the monolayers, you discover something very interesting, that is what we call a Kane and Miller quantum spin insulator. And I will discuss in a moment what a Kane and Miller model is, but for now, let's just tell you that this means that this material looks a lot like graphene, and this is what you see here with this very simple band structure. This is a band structure for the bond layer density function theory PBE without spin-orbit coupling. And what you see is that the right of the Fermi level here, there is a Dirac cone, exactly, as you see in graphene, and exactly as in graphene. If I now turn on spin-orbit coupling, and that's what I do here with the green lines, you see that there is a band gap opening. Okay, now the difference with respect to graphene is that in graphene the band gap is vanishing small, it's like micro electron volts. Okay, and that's because the spin-orbit coupling there is extremely weak. In carbon, spin-orbit coupling is really, really small. So everybody, we all talk about graphene as a Dirac semi-metal, not as an insulator. But the gap is still in principle there, just that here the effect is much, much stronger. And we try to understand a little bit why this material looks like graphene. And you start to get hints of this by looking at this model. So we did maximum localized Wannier functions that describe basically the highest occupied and the lowest unoccupied bands. So the lines that you see in the band structure are Wannier interpolation, and they perfectly match the dots that represent the direct calculations. And this model essentially is made of s orbitals of mercury with a little bit of contributions coming from the d orbitals of platinum. Okay, and these mercury atoms that are green dots here, they essentially form a buccal honeycomb lattice. So you start to see that this looks a lot like the model that you would build to discuss the pi bands of graphene, in terms of these pi z orbitals that sit on carbon. Okay. But I said, what I introduced this, I mentioned this Kane and Miller model, and here I want just to give you a little bit of introduction of what actually the model is. So back in 2005, Kane and Miller introduced this very simple tight binding model for graphene. So you have honeycomb lattice, you have a nearest neighbor tight binding hooping. And then what they discovered is that if you add spin-orbit coupling, and in graphene, this happens through a second nearest neighbor hooping that is complex, and this is the second term that you see here in the Hamiltonian, what happens is that you gap the graphene Dirac cone, okay? And then if you study a ribbon of graphene, you see the appearance of helical states localized at the edges, okay? What's special about these edge states is that essentially they're very robust to perturbations. For instance, let's say you break inversion symmetry, okay? For instance, you turn on a Rashba spin-orbit coupling, you turn on an on-site inversion, on-site term, and there is a wide region in the parameter space such that this system remains a quantum spin-on insulator. Okay. Now, of course, if you go beyond that region, okay, the system, you go out from this stability region, you gap the edge states, and you go to a trivial insulating phase. But this was actually the way the very concept of quantum spin hole insulating phase was introduced. This was where the phase, this topological phase, was introduced and defined. Okay. It was through this model and through graphene. And then later on, people realized that if you want to have a strong quantum spin insulator, there is a different mechanism you can exploit. It's called band inversion, and that was introduced by Bernavik, Hughes, and Zhang. And this led to the famous discovery of the quantum spin effect experimentally in the mercury telluride quantum wells. But this still remains the foundation of the field, and it's just that it was not exploited as an effective way to realize this effect. What we show with this material is that you can use the graphene mechanism, this Kane and Miller model, to have a robust quantum spin insulating phase. And this is what I try to show here. Here I try to show that really we have this Kane and Miller physics playing in this material. This is the band structure with spin-orbit coupling. Now I'll show you a comparison with the band structure that you get if you use a maximally localized Venn function Hamiltonian, but just the first nearest neighbor. You see, even with spin-orbit coupling, still you have a Dirac cone. You actually have to go to second nearest neighbor hopping to open a band gap in this material. And now if I turn on all the higher order hoppings, you just renormalize a little bit the band gap around K and a little bit more around the gamma point, okay? And so this says that spin-orbit coupling really comes from a second nearest neighbor hopping. What's left to assess is essentially if this hopping is really of the K and Miller type. And this is what we do here on the right-hand side. You see it's a comparison of the second nearest neighbor maximal localized Venn function Hamiltonian with the K and Miller term that is extracted from that Hamiltonian. You see they perfectly match in the low energy region. There's a little bit of deviation around gamma, and that's entirely accounted for if you include the other two terms that are allowed in tight binding as second nearest neighbor. There's a trivial real second nearest neighbor term, and then there is an in-plane spin-orbit coupling, okay? And so what these two pictures essentially put together, they tell us essentially is that in this system, the band gap and the quantum spin phase originates from a spin-orbit coupling that is a second nearest neighbor hopping term of the K and Miller type. So the same term that is in, happens to be in graphene. Now, of course, if you want to be a little bit more quantitative in terms of the band gap, you can't rely too much on PVE and DFT. So we went to G0, W0 calculations, and this is what you get. You get an increase of the band gap up to roughly a half an electron volt, which is, of course, 5-6 orders of magnitude larger than what you find in graphene, but also what you find in other honeycomb systems like arsenine or stannine or germanine, for instance. Okay, and here on the right hand side you see the spectrum for a semi-infinite ribbon with a hallmark of this topological phase. So this presence of these helical states crossing the bulk gap. But up to now, I've just discussed topological aspects of the electronic structure. Here, I just want to make the point that this material also exhibit other interesting physics. For instance, you have a coexistence of a robustness of this phase, so you have a large gap, but also switchability. And by switchability, I mean this idea that you place your material between gates, electrical gates, and through an electric field, you switch off the phase. So you switch on and off the edge transfer. And this is a little bit like what I shown you at the very beginning of my talk. So this happens in this material. This mechanism happens in a peculiar way because there is an interplay between spin-orbit coupling, crystal symmetry breaking, and the direct response. And in fact, if you study this by just you freeze your atomic configuration, you just put an electric field, nothing really happens in this material. But if you do the right thing, so you let the atoms move in the simulation, you see that there is what happens is the central symmetric structure at zero field becomes a polar structure. At final field, there is a little bit of there is a spontaneous polarization popping up, and this gives an additional contribution that helps to reduce the critical field, so helps to do this transition to the phase. So this allows to to have a large gap, still a switchable phase. And I just want to here with this want to give you a feeling that I've been discussing simulation, but this material is real, and and we are working on the experimental side to actually study this. This is an electron microscopy. Transmission electron microscopy picture of flakes, of exfoliated flakes of Jacutingate. Still not the monolayer. We have work in progress on the side. This is a multi-layer flake, but just want to show you, I think this is quite beautiful. You see this honeycomb lattice made of mercury, and then there is a platinum atom in the middle of these honeycombs. Okay, and indeed we have been igniting a number of collaborations with experimental groups from single crystal synthesis, liquid exfoliation, FM, transport, STM, Raman, optics, and ARPAS. And indeed, today I want to focus on just one of this collaboration, which is about ARPAS, which is, you see here, this angular solid photoemission spectroscopy data, because indeed, we were really interested in the monolayer and the Kane and Miller physics of the monolayer, but when we started to interact with experimental groups, we ended up studying also the bulk structure, so the three-dimensional crystal. And what we found that there was another kind of topology in the three-dimensional crystal. And what you see here is the 001 surface states that you get from ARPAS. You see this very special Dirac cones, Dirac crossings, and this were sort of a puzzle for us because we start from something that is a quantum spinol insulator in the monolayer, and the bulk is actually just a simple stack of this monolayer, so it's a layer mineral, and the standard paradigm that you can find in literature is what is called a weak topologic insulator. Essentially, you have surface states all around the sample and not on the top and bottom surfaces. Actually, what we found...
5 minutes just to...
actually what we found is that on these top and bottom surfaces, this is exactly where experiments were performed, and this is where there were these surface states that hinted a lot of some kind of topology protecting them. Okay, so Jacutin was a kind of a material with surfaces all over, direct crossing all over the place, and in particular, we show you now that there were two surface states on the top and bottom surfaces. This is what you see here. It's a comparison between the experimental RPS data and the dense function theory simulated spectral density. And you see there is very good accuracy. So the agreement is very good between the two, between experiments and theory. And we actually discovered that there is actually a mirror number, so protecting this phase, what we call the topological crystalline insulator, essentially. And this was also independently, this simulation was also independently performed by other groups. I put the references here. And so this explains why that these surfaces are topologically protected by a crystalline topology, but doesn't explain why this happens in a sense. So what we wanted really to understand, how do you go from a monolayer that looks like graphene, has this quantum spin phase, to a three-dimensional system where this gap at K basically disappears. It goes back almost to a Dirac cone. There is dispersion along the outward plane direction, and then there is this mirror number appearing in this crystalline topological phase. And we explain this with one simple extension of the KNML model. So again, we came back to this maximum mechanized Vanier function technique. We apply now to the crystal, to the bulk three-dimensional crystal, and we show that the strongest coupling after in-plane nearest neighbor is one term that couples one Vanier function, so one layer, and the other layer, this sits basically two layers above or two layers below. That's the strongest term. And this essentially decouples the even and odd layers, and that's what you see here on the right-hand side of this slide. Okay, so with this one single term, which is actually very strong, you can explain all this emergent crystalline topology. So you see here, this is a scan going from lambda equals 0, so from zero coupling, so to graphene, basically graphite, and to lambda equal 1, so to the bulk Jacutin. On the top panel shows the slab and structure, and you see that you start from something that has a Dirac cone, so it's graphite, graphene, and the more you increase your coupling, you start to see that there are surface states, the red states appearing. There is a new Dirac cone appearing, okay, and this is mirrored by the appearance of a Zach phase. And indeed, you can explain all of this by saying that essentially the surface states are the bound charges. So if you want, is due to a polarization, and that's what the Zach phase is computing, of effective one-dimensional tight bonding models along the stack direction, essentially. And of course, you can make the model a little bit more complicated. You can add spin-orbit coupling. And of course, now you have to abandon the Zach phase, and you use instead what's called a mirror number. And you see you can compute it, and you have a mirror number -1. And that you can ask why it's -1, why 2 minutes ago you said it was -2, essentially because, as I said, this model decouples even and odd layers, okay? And once you put together all the, you put back all the couplings, okay, you start to include the nearest layer and particle symmetry breaking, okay? Now you have a mirror number equal -2 or 2, and you have this a pair of surface states, okay? And this is actually in very good agreement with what you see in experiments, essentially. And with this, I just want to sum up a bit. So I'm trying to show you how this mineral, Jacutin, is very interesting. So you have monolayers that are large gap quantum spin insulators with Kane and Miller physics and a switchable topological phase. How if you study the three-dimensional parent crystal is actually one of the rare examples of dual topological insulators. So you have both a Z2 and a crystalline topology, and this is confirmed by ARPAS experiments. And finally, I just want to mention there are several ongoing, also independent from us, theoretical and experimental efforts have been going on after our initial discoveries here that I presented today. The latest one, just something that I found a couple of days ago on the archive, that shown that experimental, actually, this material becomes a superconductor, high pressure, while maintaining its topology and its surface state. So, I think this material will keep on being fun to investigate for in the short future. And finally, I just want to acknowledge my collaborators. This is the theory and simulation team: Marco Gibertini, Davide Campi, Nicola Moni, and Nicola Mazzari. And here on the right inside, you see some of the experimentalists we collaborated with. And finally, I want to thank you for your attention.
Thank you very much, Antimo. So in the name of everyone who you cannot hear, let me clap in the name of our 600 people who are listening. Okay, so thank you very much. We have had 2 questions typed in by Sonia Haddad. So let me see. Sonia, can you say something? I think we should be able to hear you.
Hello, everybody.
Yes.
Thank you. So, hi, everybody. I'm from Tunisia. So I'd like to thank all the organizers for this nice workshop. So I have a question about your topic. Actually, I was wondering what is the origin of the complex next neighbor hopping in this compound, and especially how to confirm that they are really this sort of local magnetic flux field in the system.
So regarding the first part of the question, so the reason why this happens is essentially because you're building this maximum correct Wannier function model, and you discover that the Wannier function becomes localized on 2 layers. Essentially, you see it probably here on the right-hand side of the picture. You see it's spread all over 2 layers, so it's a bit delocalized, and so it's a method of geometrical interference. When you start to see the overlap between Wannier function, you see that it's very favorable, this overlap between these 2 Wannier functions that I picture here, that are somehow aligned geometrical because of the angles of the between mercury and platinum. Okay, so it's due to the fact that this Wannier function is quite localized in a sense. And I didn't fully understand the second part of the question. If you said the magnetic flux, the system is not really magnetic here. It's as I said, it's a non-magnetic system. So you have what's driving the everything is basically spin-orbit coupling. Okay, and actually what you see here is that if you are in the layer, so in the monolayer or in the bulk, again, due to different interference effects between different possible hoppings, you have a cancellation or not of the Kane and Meyle spin-orbit coupling term. So this is why actually in the 3-dimensional bulk, you don't really have a Kane and Meyle, a strong Kane and Meyle term, essentially.
Okay. So thank you very much, Antimo. So we have 2 more questions, but I've been warned by the organizers to stay perfectly in time, so I will try to do my best. I'm sure that Antimo is available for questions also later. I mean, we are aware that this online format is difficult for communication, but we hope that later, for example, in the poster session and so on, you will have many more occasions to discuss with people, and you can contact Antimo by email or anyway. Okay, so thank you very much again, Antimo. Okay, so we come to the second talk. Can you perhaps already share your screen, Miguel, so we can see?
Yes, I proceed right now.
So the next speaker is Miguel Royo-Valls from Spain, and he will talk about first principle calculations of bulk flexo or the bulk flexoelectric tensor. Okay, so please, Miguel. Also in your case, I will tell you 5 minutes or so before.
Okay. Thank you for the presentation, and hello everyone. The work that I'm going to show you here today has been developed in the group of Massimiliano Stengel at ICMAP in Barcelona, and it can be considered as a sort of culmination of a continuous research on this topic for over 10 years and involving several people apart from Massimiliano Stengel and myself. So, in order to introduce flexoelectricity, let me compare it with a more familiar electromechanical coupling, such as piezoelectricity. Piezoelectricity is the macroscopic polarization response to a uniform strain, and is a property which is only displayed by crystals that have a non-centrosymmetric structure. Therefore, few materials have this property. Flexoelectricity, in turn, is the macroscopic polarization response to a strain gradient deformation, such as a bending of a material as illustrated in this figure. The interest lies in the fact that flexoelectricity, being described by a force rank tensor, which is this flexoelectric tensor, is a universal property of all the materials. And moreover, it is expected to become more and more relevant at the nanoscale where large strain gradients can be sustained by the materials. The first applications of the flexoelectric effect were basically aimed at finding cheaper replacement for piezoelectric materials. However, more sophisticated applications have been reported over the years, which often exploit specific properties of the flexoelectric effect. Here I have shown a few examples, which include the possibility of mechanically manipulating the polarization in a ferroelectric by application of a external strain gradient with the tip of an atomic force microscope, or the possibility to modulate the transport properties of a two-dimensional electron gas accumulated at an interface by bending the heterostructure, or the observation of an increase in the photocurrent generated in a photovoltaic device when, again, a strain gradient is applied by means of a strain gradient deformation is applied by means of the tip of an atomic force microscope. In spite of these sophisticated applications, our fundamental understanding of the flexoelectric effect is far from being complete. And the first principle theories are a valuable alternative in order to shed some light in this problem. Because in an experiment, one typically does is to bend a sample and measure the transient current. However, the problem is that the result of this measurement can have several contributions from the bulk of the material, maybe from the surface of the sample, but also if there are domain walls or defects in the sample, they can also have a finite contribution to the flexoelectric response. And in an experimental measurement, only the overall summation is accessible. In this sense, density functional theory can be considered as a theoretical microscope that will allow us to individually isolate these contributions. However, flexoelectricity is a very challenging problem when it comes to be studied from first principles. And the main complication comes from the fact that a strain gradient deformation breaks translational symmetry, which prevents us, in principle, to use spatial periodic boundary conditions that are typically assumed in most first principles theories. A possible solution for this problem comes via the use of acoustic phonons near the gamma point or in the long wavelength limit. As we can see in these two figures, the atomic displacements associated with a longitudinal acoustic phonon or a transverse acoustic phonon in the right remind us to the macroscopic deformation associated with a strain gradient of the longitudinal type or a shear strain gradient in this case. This means that somehow we can extract the necessary information to study flexoelectricity from acoustic phonons. And this is basically the approach that Richard Martin took in the 70s in order to study piezoelectricity, and later 10 years ago, this group of authors used to attack the problem of flexoelectricity. More formally, the method consists in describing a macroscopic deformation by means of an acoustic phonon, which is nothing but a deformation wave which is modulated by a phase at a given wave vector q. Then the method consists in expanding the response to this deformation wave in a Taylor series in the y vector around the gamma point. In this way, at order 0, the polarization response vanishes due to the acoustic sum rule, whereas at first and second orders in Q, we recover the necessary information to study the piezoelectric and the flexoelectric effects. Moreover, this approach has a crucial advantage, which is that we can perform all the necessary calculations on a primitive cell by using the tools developed for the density functional perturbation theory. In the practice, we need to deal with a few intermediate quantities, all of them enjoying a similar Taylor expansion in terms of a translational, a uniform strain, and a strain gradient deformation. The first one is the electronic polarization induced by the acoustic wave. Then we have the atomic forces, which at first and second order provide us with the piezoelectric and flexoelectric force response tensor. And then we have the atomic displacement that give access to the internal strain tensor, both the piezoelectric and the flexoelectric one. Also, in order to simplify the notation, in the next slide, I will assume this bracket convention to describe some lattice-mediated tensors that depend on a sublattice index and a Cartesian index. For example, for the bond effective charges given at a polarization direction alpha, I will represent them as a 3n dimensional vector. Then, for example, for other quantities such as the force constant matrix, it will be represented as a 3n times 3n operator. Okay, with these ingredients, we can write a very similar formula for both the piezoelectric and the flexoelectric tensor. And they are shown here, and as you can see, in both cases, the response can be split in an electronic and a lattice-mediated part. The latter is calculated from the product of the bond effective charge and an internal strain tensor, which, as I said, describe the atomic displacements induced by the deformation. These internal tensors can be in turn computed by multiplying the force response tensors with the pseudo-inverse of the force constant matrix. For the case of piezoelectricity, the composition stops here because both the electronic piezoelectric tensor and the force response tensor can be directly calculated from density functional perturbation theory. However, the analogy with flexoelectricity stops here because for a flexoelectric case, both the electronic flexoelectric tensor and this force response tensor are not elementary quantities, but they can further decompose in a clamped ion contribution, which is shown here, plus an additional term, which is written in terms of the uniform internal strain tensor. So to understand the physical meaning of these additional terms, consider a crystal in which there exists an optical phonon mode which couples linearly to a strain. Here, this optical mode is represented by means of this red double arrow. And in case of a centrosymmetric material, this would be typically an even mode and will be related with the Raman activity. Then a strain gradient on this material will induce in turn a strain gradient of the amplitude of this Gerade mode. And at the same time, this gradient of the Gerade mode will produce, on the one hand, an electronic polarization, which in our formalism is quantified by this P1 tensor, and on the other hand, a set of non-zero forces on polar modes, which are quantified in this Phi1 tensor. So this can be interpreted as an indirect contribution to flexoelectricity, and it will be active, for example, from the presence of Raman modes as the Raman mode of silicon, or from the oxygen octahedra tilt that occur in perovskite oxides, as I will show you in few slides. So at this point, let me review which response functions we can calculate in terms of density functional perturbation theory with a first principle code such as ab-initio. These are written as a second order derivatives of the total energy with respect to an electric field, a phonon, or a strain perturbation. And the resulting uniform response functions are well known. They are the dielectric tensor, the force response tensor, or the elastic tensor when the two derivatives are taken with respect to the same perturbation, or the Born effective charges and the clamped ion and force response piezoelectric tensors when two different perturbations are mixed in the second derivative. Recently, we have extended the capabilities of the density functional perturbation theory in order to calculate a new set of linear response properties. These new properties can be considered as the spatial dispersion of the uniform ones. And in this case, they are written as third order energy derivative with respect to two of the previous perturbations and a third derivative with respect to the momentum y vector. These are the new tensors that can be computed following this approach. And the red ones, the calculation of the red ones has been already implemented in ab-initio. And indeed, these 4 tensors are the new quantities that we need to calculate in order to build the bulk flexoelectric tensor. There are also these additional 2 spatial dispersion tensors that are related with the natural optical and acoustical activities, whose implementation is underway. Okay, to illustrate the performance of our approach and implementation, I have applied it to the case of cubic strontium titanide perovskite. In this system, there are only 3 linearly independent flexoelectric coefficients that are shown here in the table, which describe the polarization response to a longitudinal strain gradient, to a transverse one, and to a shear strain gradient in the 3rd row. And I have shown in the rightmost column the total bulk flexoelectric coefficients for these 3 cases, whereas these 4th columns show the decomposition of each contribution. In the 1st and 3rd columns, I'm showing the clamped ion contributions to the electronic and the lattice-mediated flexoelectric tensor, and in the 2nd and the 4th column, I'm showing that indirect contribution that was active in the presence of Raman active modes. As you can see, for the case of this high symmetry material, these indirect contributions vanish due to the high symmetry of the crystal. But what occurs if we take a look at the lower temperature polymorph of this of the strontium titanide, which is in this case a tetragonal crystal in which the oxygen octahedra experience this sort of antiferrodistortive tilts over the plane, which is perpendicular to the tetragonal axis, as illustrated here in the left figure. In this case, we see how now there is a finite contribution by means of these indirect terms, which is the consequence of what is called rotostriction, by which the tilts of this octahedra are directly coupled with uniform strain.
Miguel, it's 5 minutes or so.
Okay, thank you. So at this point, one would be tempted to analyze further these numbers. However, I must say that this analysis would be worthless, and the reason is that, the reason is that the longitudinal and the transverse coefficients are ill-defined. So these numbers are only do not have a clear meaning. Only the shear ones that are shown here and in these 3 bottom rows are free from this problem, as I will explain in the next slide. So the problem is that the bulk flexoelectric coefficients are only defined modulo a constant that can be written in terms of the dielectric susceptibility and the linear variation with the strain of a potential or an energy. And this is originated due to the necessity of removing the macroscopic electric fields that are associated with phonons in the long wave limit in the calculation of the flexoelectric tensor, which in the practice boils down to impose short-circuit electrostatic boundary conditions in the calculation. This is really necessary because otherwise we cannot even write the flexoelectric tensor as a tensor. Then the problem appears because when imposing these short-circuit boundary conditions, we need to assume a reference potential, and the final result will depend on this election. This is originated because in the presence of a strain gradient deformation, the different energy levels of the system will experience a different tilt as a consequence of the deformation, which is something that I have illustrated here with for a slab of a material in the presence of a strain gradient deformation linearly increasing in this direction. As you can see here, I have illustrated the conduction band minimum and the valence band maximum and the average electrostatic potential. In our implementation, we have taken as the potential reference the electrostatic potential, but this is an arbitrary choice which we made just because of practical reasons, and one could obtain similar results or still valid results adopting one of these other 2 energy levels. So at the end, the meaning of this additional undetermined term is what we need to add to our calculated flexoelectric tensor in order precisely to shift this potential energy reference, which is directly related to the theory of absolute deformation potential, and demonstrates that we can also access this other physical property by means of our implementation in ab-initio. So now the reason why the shear flexoelectric coefficients are free from this ambiguity is that in our approach, the shear coefficients are extracted from the atomic displacements associated to a transverse phonon mode. And a transverse phonon does not generate macroscopic electric fields, so one does not need to worry about them. To conclude this presentation, let me say a few words about the surface contributions to the flexoelectric effect. To this end, let's consider a sample of a centrosymmetric material with surfaces, a finite sample. And in this centrosymmetric material, however, the surface will be always piezoelectric because there the centrosymmetry is locally broken. Then, when one applies a uniform strain on this slab of a material, the induced dipoles at the two opposite surfaces will compensate each other because they point in opposite directions, and the result is that we do have a zero macroscopic effect in total. But what occurs for the case of flexoelectricity? For example, if we bend this slab, as shown here, now the local strain at these two opposite surfaces is anti-symmetric. And because of this, the induced dipoles at the surface will point in the same direction and will contribute to the total flexoelectric response of the slab. Actually, today, we know that the surface contributions can be as important as the bulk ones at any thickness of the sample. For example, in this paper, it was shown that the surface and the bulk contributions have an opposite sign, and they cancel each other, to the point that the configuration of the surface can even lead to invert the sign of the final total response to the deformation. Moreover, the surface terms have an interesting property. They can be obtained as the linear variation with a uniform strain of the potential offset generated at the surface. And the thing is that this quantity suffers from the same reference potential ambiguity that I have shown you previously for the bulk flexoelectric tensor. However, it enters with opposite sign, which at the end leaves us with a total flexoelectric tensor, which is the sum of the bulk contribution and the surface, which is well defined as it should be. In case you are interested in learning more about how to incorporate the surface contributions to flexoelectricity in following our approach, take a look at the poster 130 by Matteo Springolo. So to conclude, we can finally enjoy an efficient implementation of the calculation of the flexoelectric tensor. One can go to the ab-initio web page, download the code, and run the simulations. However, the take-home message here is that the numbers that one would obtain in this way are not really meaningful. One always needs to add something to them in order to obtain a measurable physical observable. And this something can be a band term, which provide direct access to the absolute deformation potentials of the material, or a surface contribution, which gives access to the total flexoelectric or voltage response to a deformation gradient. That's all. Thank you.
Thank you very much, Miguel. So I'm sorry for this meager one-man clapping. Okay. So as it is very nice that Miguel has already introduced the poster 130, as we remember, where people can ask, obviously, then in a more informal setting, more questions about this. We have now had one question by František Herman. Let me see. Can you say something, František?
Yes, sure. Thank you
Okay.
very much. Okay, I see you hear me. Thank you, Miguel, very much. I have one question. Are there any materials having Van-Hove singularity as flexoelectrics? And what are the effects then on observables? Thank you very much.
So can you explain me what is a Van-Hove singularity, please?
Yeah, the Van-Hove singularity means once you hit the boundary of the Brillouin zone with the Fermi surface, so you get large amount of states, like when you have superconductivity in graphene.
Okay, you are talking about metals.
Yeah, for example.
Okay, yeah. All the theory that I've shown here is valid for insulators.
Ah, okay.
Just for insulators.
Ah, okay. So you have no metallic structure there.
Yeah.
Okay, thank you very much there.
Okay, so I think we can have a second question by Sayed Husseini. 1 minute. Can you say something to see if we hear you?
Hello, can you hear me?
Yes, we can hear you.
Okay, thank you very much for your nice talking. I'm gonna understand the behavior of flexoelectric tensor by increasing the layer. Is there have any a special behavior for this or not? Increase the layer in two-dimensional materials.
Yeah, the layer thickness, do you mean?
Yes, exactly.
Yeah, well, as I said, the bulk and the surface contribution tend to compensate each other because they have opposite signs. So both of them will increase with the thickness of the sample. What we have observed, well, not directly with this implementation, but in previous calculation, is that this compensation tends to a finite value. So it converges to a finite value, which is the total flexoelectric response of that to that kind of deformation. So there, yeah.
Okay.
So in some, in some materials like MOS2, when we go from bulk to two-dimensional material, we observed piezoelectricity. Is it true for flexoelectricity or not? Thank you very much for your answer.
Okay, well, flexoelectricity is always in any crystal, no matter the underlying crystal symmetry or not the dimensions of the sample. But we observe when we go from 3D to 2D,
yes,
in the flexoelectric tensor is a reduction of in the magnitude of the flexoelectric tensor. However, this doesn't mean that flexoelectricity is not important in 2D materials. It's just the opposite, because in 2D materials, okay, the flexoelectric tensor might be small, but the strain gradient deformation that this 2D material can sustain without before fracturing is much larger than what can occur in 3D. So that's the reason why normally one says that flexoelectricity is relevant as the size scale is reduced.
Thank you.
Okay, so thank you very much. And I'm sorry for the other people who have indicated that they have some questions. Perhaps you can later discuss with Miguel at this poster, which will come up later. Okay, so thank you very much again, Miguel, for this nice talk. And now we come to the last two talks of this session, which are both about a topic which has gained more and more importance in recent years, which is machine learning and neural networks and so on. So if we can perhaps already put up the slides. Yeah, can you share your screen perhaps?
Hi everyone, so you can hear me?
Yes.
So do you see my screen?
Yes, we can see it very well. So the next talk is by, I already have to say sorry for certainly pronouncing wrongly your name. So it's by Nook Achtrit, is this right, more or less?
That's called a mean non-attribute, just non. That's enough.
Okay. It is by Nonge from Columbia University, and she will tell us about training in neural network potentials, including atomic forces via Taylor expansions. Okay, so please go ahead. And as the other ones, I will tell you, so 5 minutes or so before the end of your presentation. Please.
Sure. Thanks. Yeah. Hello, everyone. Thanks, Rob, for the kind introductions. Thanks the organizers for organizing the Great Total Energy Workshop. Thank you for having me as part of this, and also thanks everyone for joining us today. So my name is Nong Atrit. I am a research scientist in the Department of Chemical Engineering at Columbia University as part of Columbia Center for Computational Electrochemistry. So in this talk, I will discuss our recent development on the efficient training of neural network potentials by including atomic forces via Taylor expansions and application to water and transition metals, oxides. So this project is in collaboration with Dr. Cooper, Dr. Keisner from Stuttgart University, Germany, and Dr. Urban from Columbia University. So accurate simulations of large-scale systems is important, right? DFT methods provide accurate energy and forces, but to access real-world complex systems, efficient and accurate interatomic potentials are needed. So in this talk, I will focus on machine learning models for large-scale MD simulation. The general idea of machine learning potentials, or MLP, is to use machine learning methods to representing the potential energy surface, or PES, in this short term here, from accurate energy methods, for example, quantum mechanics database. And the resulting of the MLP can then be used in MD or MC simulation. Our approach uses artificial neural network for the interpolation because they can be very accurate and can be trained on large data sets with hundreds of thousands of data points. The models only need atomic positions and are reactive and full dimensional, but it takes a bit of effort to construct and to validate them before we can then be used in the intended applications. We follow the general idea of the high-dimensional neural network potential methods by Baylor and Parinello. In these methods, neural networks are trained to predict atomic energies, and the total energy is given by the sum of all atomic energies. The input for each single neural network is a description of the local environments of a single atom or structural fingerprint. This structural fingerprint usually describes the local environment within a radius cutoff of 6 to 8 angstrom, depending on materials. The neural network predicts the energies contribution of one atom, and the total energies is the sum of all atomic energies. Here is an example of a simple atomic energy feed-forward neural network. On the left-hand side, this simple feed-forward neural network has 3 layers. Input layer, hidden layer, and output layer with artificial neurons or nodes, like represented here. So input layer, hidden layer, and output layer. For our applications, the input layer describes the local atomic structures, and the output layer is atomic energies. The number of nodes in one or more hidden layers determines the model complexities. The equations here on the right-hand side corresponds to the same 3-layer neural network. The atomic forces can also, the atomic forces can be calculated from the analytical derivative. In this equation, so each node or artificial neurons of the neural networks applies a nonlinear activation function. This is an example of the hyperbolic tangent. So descriptors for local atomic environments important. The fingerprint or descriptor used by our neural network potentials is based on an expansion of a local RDF and ADF in the basis sets of Chebyshev polynomials. Here, phi alpha, you can see here, is the Chebyshev polynomials of order alpha, and C alpha is the corresponding expansion coefficient. The local atomic structure, as you can see here, with the coordinates of all atoms within the cutoff or RC, which is described by two sets of coefficients, one for the bond length, RDF, and one for the bond angle, ADF. A second set of weight coefficients is used to capture the local atomic compositions or atom types, T, or chemical species. Here, W, or weight of atomic types or species. So we represent this as the element specific. Sometimes it's easier to look at equations than just cartoon that I just showed in the previous slides. Here are the equations of the Chebyshev descriptors for the local chemical species or atom type T. The descriptors components are the expansion coefficients of the RDF and ADF. So the weight WTJ are specific for atomic species. The descriptor of local structures is equivalent, but all of the weight atomic types or species are equal to 1. So far we discussed machine learning potential trained on energy only, but for MD simulations, atomic forces are also important, right? So in this paper, we did propose an efficient approach for training neural network potentials, including atomic forces via Taylor expansion. Neural network potentials can efficiently be trained on total energies, but small, accurate reference datasets often lead to an potential with significant really force error or large force errors. So increasing the dataset improve both the absolute values on the left here that you can see, and on the directions on the right figure of the predicted forces. Here on the left, you can see that the tail of the error distribution disappear with when we increase the number of data points. And the predicted directions of the forces vector also improve with the data size increasing, especially for the small force vectors. In principle, neural network potentials can be trained on total energies and atomic forces. Energy training, RE, is a loss function that minimized during energy training. This function is contained the difference of the predicted and reference energies. Here is the additional loss function term for the force errors. Note that the forces acting on atom J is a negative gradient of the energy with respect to the with the positions of atom J's. So both terms can be combined and trained on energy and forces at the same time. Here, as you can see here, AE and AF, they are the relative importance of the energies and forces error. Conventional neural network training methods make use of the gradients of the loss function. Neural network potentials can be efficiently trained on total energies, which it requires only the first derivative of neural network potential energies. Force training with gradients require a second derivative of neural potentials. This makes forces training more computationally demanding and very expensive, and also required much more memory, which is can be really an issue for large neural network architectures. Additionally, we also looking at the radial cutoff for the force evaluation, which is twice larger than for energy evaluation. The atomic energy depends on all atoms within the local atomic environment. So this means within the cutoff distance RC, sorry. From the central atom I, so however, the forces acting on atom I depends on all atoms within twice in this distance, so like a 2 RC. So for further discussions on these methods, you can also see our previous publications in PRB 2012, where we also provide durations here. So this scale make force training computationally very expensive for such as condensed phases. This is why we developed an efficient approximation of the force training approach. So we use Taylor expansions to estimate the energies of structures with small displaced atoms. So on the left here, we have only the energy training only. So we would like to reproduce the energies in the gray curve here, having the reference data sample as a blue. And after use neural network for predict the energies, you can see that it looked like our neural network training fitting very well, but predict wrong bond length and also energies. But when we include forces information in the training set, we introduce more points, more data points using Taylor expansion, and we predict our energies using neural network prediction. So we predict the energies curve that we, the target energies accurately. In our approach, additional atomic structures are generated via random displacements of atoms in one of original structures. So the optimal magnitudes of the displacements is system dependent. For example, in this case, we use a water cluster. So a displacement of around 0.01 angstrom works quite well, as you can see here in figure. But with the number additional structures in this plot that I have it here, the number, this means the number that we introduce to additional per original structures. The x-axis, this is the maximum random atomic displacements, and this is a mean absolute error of atomic forces in percent. So the more additional structures that introduced by the Taylor expansions is look like the more accurate, but also depending on the maximum random displacements. So in this case, for water, 0.01 angstrom show the best performance. So note that when it works, actually direct force training can be more accurate than the Taylor expansion. For small 6 water cluster system, direct forces training require 8 times of the CPU time higher than training with just using our Taylor expansion methods. Like you can see here, the green and the blue, this is the Taylor expansion, but the black, this is the direct for trainings. But as I mentioned already, for condensed structures or periodic structure, direct force training for all force components is typically very challenging or not feasible. We also tested the approach for a more challenging system. This is the system that we selected, a lithium ternary metal oxide with 5 chemical species. For such a complex composition, it is challenging to compile really large reference datasets for neural network potential fitting. So approximate force training can be reduced the number of reference structures that is required to construct such a complicated neural potentials for these 5 chemical species. So as you can see in the left figures, the optimal atomic displacement for the Taylor expansions is around 2 or 3 times larger than for the water that I showed in the previous slide, which makes sense because of the atomic distance or bond distance are around 3 times larger than water, like a OH or OO in the structure of water. So
long it's 5 minutes or so.
Thank you. Yeah. Approximations or approximate forces training remove the high error tails from the error distributions. This is expected to improve the stabilities of the potentials or neural potentials for MD simulations. Here, to test the improvement, so we perform around 1 nanosecond long MD simulations. This test, we use a small number of reference dataset, 800 reference structures. Actually, the 800 reference structures are not sufficient to obtain a good neural network potentials by using energy training only. So the MD simulations are not stable, as you can see here on the red and yellow MD trajectories. But training with Taylor expansions methods with the same data set, so you can see on the green trajectories, it looks like our MD simulations is more stable, right? So these primary potential neural network potentials we still need for further refinements for the real applications. This is just to show as an example. The Taylor expansion methods has been implemented in our open free source code A-init package. It will be made available with the documentations in the next A-init release. Just to let you know that A-init is free to download from this website and also provides a library that you can really use the interface with standard software for MD and MC simulations, for example, ASE, Tinker, or LAMP. In summary, so I hope I could demonstrate that using the force training approach, the size of the reference dataset can be smaller since more pieces of information per structures are used in the training set. So this means less actual, for example, DFT calculations are needed. It makes it's also easier to construct preliminary neural potentials for MD simulations. Training on small data sets is already show for the cases that I show that already produce neural potentials that are stable in MD simulation. So finally, I would like to acknowledge my collaborators and facilities. Many thanks to the current team members who are now working on machine learning models for energy materials. So Shen Wang and How You Go. Thanks also to the current collaborators on other machine learning projects. So April Cooper from Stuttgart. Also, thanks Dr. Shen, Dr. Urban from Columbia University, and Dr. Hybersons from Brookhaven National Lab for the discussion. Michael Shen and Professor Tom Markland, Stanford, also help us to implement A-init and LAMP for MD simulations. Also thanks Professor Keisner, also for the force training by Taylor expansion these methods. So thanks again to the organizers. Thank you, you all for your attention. If I still have time, I'm happy to take questions and comments.
Okay, thank you very much, Nonge. A very nice talk. Yes, we have some time for some questions. I think we will start with Amir Talebi. You should be able to speak now. Can you say something, please? Amir? Your mic, yes. Please say something. We cannot hear you right now. Okay, apparently you have problems with the microphone. Then perhaps I can just read the question, which she has written. The question is, which potential did you use to get your data using the DFT?
So for water, we use a B-tree and plot some kind of like a long range and charges. So April Cooper is produced the reference data for the water. And for the 5 chemical species, lithium tungsten metal oxide cathode materials, we're using the scans functional. This is the new method that we use it.
Okay, thank you very much. And then there is Kan Antaka who has some question. Let me see, allowed to talk. Can you say something, please, just to see?
Hello, can you hear me?
Yes, we can hear you. Please ask your question.
Yeah, so I actually have 2 questions. So the first question is the descriptors that you're using. So what I see is it works well for 3-dimensional bulk structures. So I wonder, will it generalize to 2-dimensional materials, or it never just have been tested on 2-dimensional materials?
Actually, there is no, I mean, from general methods here, there is no way or no problem to prevent to work with the 2D materials. So we have done so far mainly for molecules like a water or gas phase. right? It's also like a smaller dimensions, and condensed matter, like a 3D, like a periodic lithium tensor metals. For 2D, I believe that you maybe have only, I mean, you have to think of like in case of the maybe less number of directions, for example, the angular, that you can also put it in the way. So in my opinion is that our descriptor should be general for any kind of systems, including the 2D materials. I haven't done any, I have no experience on the 2D material myself. I'm not sure, but maybe you could try.
Okay, thank you so much. So like, if I can ask another question. So
very quick, please.
Okay. So my second question is about how hard, or like if you like, what are the basic guidelines that you take when you are trying to sample the data points for creating your training data set?
This is very good questions, and I always got these questions. So the selection is really depending on your intended applications, right? You have to make sure that you selected your reference data can really represent or sampling that cover the energy range and forces to cover your potential energy surface that you can really use in MD or MC simulations. So it depends. You can have a small reference data points or larger different data points. It depending on the complexities of your materials, and also depending on the applications.
Okay, thank you very much.
Thank you.
Perhaps we can close this with one very quick question from myself, which is, so I would like to know, when you learn forces and energies, is it kind of assured that one is always the exact derivative of the other? Because otherwise the problem might be that you get drifts in energy or so when you do molecular dynamics. No?
So, okay, you're saying is like if I train that if I have accurate energies, maybe the forces is not accurate. Is that?
No, I mean, since you learn both not perfectly exactly, but to very good approximation, as you've shown. But I mean, is one really always the exact derivative of the other?
For this case, it is not, right? As I show you our methods here, this is just to estimate the gradient of your structure that you increasing as a Taylor expansion. This is just to introduce the gradient as usually this is kind of still the energies, but you estimate how the forces should be when we start to introduce such a small atomic displacement on the structures.
Okay. Okay, I think we would have to discuss this a bit more in length. Okay, so thank you very much again for this very nice talk and this contribution. And I'm sure that you're also available to all participants if they want to ask more questions, because I see we have many, many questions which could not be asked.
Send me emails. I'm happy to discuss and respond all questions. Thanks very much.
Very good. Thank you very much. Okay, so we come to the last talk of this session. It's again about machine learning. Our speaker is Guillermo Mazzola from IBM Research in Zurich, and it's about machine learning physics for dense hydrogen. Okay, please go ahead, and I will interrupt you 5 minutes or so before the end, as before.
Okay, thank you very much. Thank you very much for having me here, because this is very special for me, because the Total Energy was my first conference that I attended in my life when I was a first-year PhD student in CISA 10 years ago. So I'm very happy that I have the possibility to present today this work. Now my daily work in IBM Zurich is quantum computing, but here I want to show you some progress on a physical system that I studied since my PhD, indeed, the dense hydrogen, using a new technique, machine learning. So let's go to the outline. First of all, I hope that you can see my screen, right?
Yes, we can see.
Okay. So I want to keep this talk quite simple and high level. So I want to provide you a brief overview of why dense hydrogen is still studied today. Then I want to show you this machine learning power simulation that are conceptually the same that we just saw in the previous talk, and then see if this enable us some new computation discovery on this long study system. So the motivation to study dense hydrogen today are essentially three. So dense hydrogen is still a fundamental interest in condensed matter. For example, Ginzburg placed understanding and synthesized hydrogen metallization as a top three problem to be solved in this century. So above dark matter, for example. But this system is very complicated because it lies at the interface of lattice model and materials modeling. So you have still strong correlation, but also the complication arising from real materials. So for example, nuclear quantum effects. As a result, you have a lot of phase transition, which are structural, but also electronic. And this makes the problem very hard also from the theory. Then technological application for hydrogen are also important. We know that last year, finally, a room temperature superconductor has been discovered. This is indeed a dense hydrogen system at megabar pressure, which are exactly the same that I'm going to talk in this study. And indeed, is also these megabar pressure are the pressure that are happening inside the giant planets like Jupiter and Saturn. Therefore, the physics of dense hydrogen is deeply connected with planetary science. So let me walk you through the most recent phase diagram, and this situation is rapidly evolving because, as I say, this is still ongoing experimental and theoretical effort on this system. So at, let's say, relative small pressure, the hydrogen is described as a system of molecules. So there are molecules, fluids, and in a low temperature, the solid, which is the blue region. And upon compression, has been predicted almost 1 century ago that hydrogen should metallize. So we should have metallic hydrogen. A lot of experimental effort has been put forward to see metallic hydrogen, but until 300, the molecule is still insulating until 300 gigapascal, which is this blue to white boundary on the right. What has been instead synthesized, or at least observed, is metallic hydrogen in the liquid phase, in this although this black point, although the position and the mechanism of metallization is still debated. Another important feature of the phase diagram of dense hydrogen is the reentrant melting line. So if you place yourself at 800 Kelvin, or at this type of pressure, if you compress the solid, you have again the liquid. And as a matter of fact, the region in which the molecular fluid, the atomic fluid, and the solids intersect or meet is still unknown. So experiment cannot reach this pressure at this temperature, and also theoretical methods are very challenging to be. Prediction driven by theoretical methods are not so simple. Indeed, the path to metallization, also in the molecular solid, is still unknown. This is why the problem is interesting. Indeed, what I show you here as a blue region is indeed a collection of a lot of phase boundary in the solid, which are, we know the phase boundary experimentally, but the crystalline structure are difficult to be understood experimentally because of weak X-ray scattering. And there are a lot of competing experiments that claims to observe hydrogen metallization at different positions in the phase diagram. As a result, there is still a lot of questions going on about how and where hydrogen will metallize, realizing the dream of Wigner and Huntington. Finally, the connection with planetary science is clear. So the adiabats of Jupiter and Saturn cross the metallization, the proposed metallization transition in the fluid. Namely, there exists a metal to insulation transition in this planet. And the character of this metallization is really important because, let's say, planetary modelers desperately need a first-order transition somewhere to justify a posteriori their 3 layers model for this planet. And the metallization of hydrogen has been always postulated as a boundary between the outer and the inner liquid hydrogen layers. And moreover, the metallization should trigger several phenomena. For example, helium rain, which is a mechanism postulated to explain the anomalous luminosity of Saturn. So helium should demix in metallic hydrogen, creating droplets that falls inside the planets, eating again the planets and explaining this excess energy that we see and makes Saturn looks 2 billion years younger compared to what it should. So the physics of hydrogen is deeply connected with planetary science in several ways, and this that justify the fact that we are only looking in this talk at the liquid-liquid phase transition. Indeed, this transition is still debated. There are experimental observations by different groups that are scattered on a 200 gigapascal range or 2 megabar pressure range. So, how does this experiment differ? So they use different proxy to signal a first-order transition, for example, reflectivity or heating curves, and they also use physically different methods to compress hydrogen. But if we assume that there is one first-order transition, this should not matter because only one line of experiment should be correct and the other should have some systematic error due to the experimental process. So therefore, a lot of effort has been put forward from a theoretical side to try to assist this experiment using first principle molecular dynamics. Unfortunately, this system is very challenging because, as you see, if I change the electronic solver, also within the FT, if I use PB or van der Waals functional, my prediction for the metallization differ by order of 100 gigapascal. At least what all the simulation method agree is on the character of this transition, which is first order at least below 2000 Kelvin. So while the position is still debated, at least the theory agree on the existence of a first order liquid-liquid transition. So in this talk, instead, I will provide evidence for the opposite. Without even claiming that the problem was in the electronic solver. So what we saw is indeed that the problem are in the first principle molecular dynamics setup itself. Indeed, what do you do when you want to probe this kind of phase transition? You perform first principle molecular dynamics with PB, for example. But it's also true that there is an ambiguous distinction between a liquid and a defective solid if the size is small. And it's also true that a picosecond long simulation, which are standard for the normal DFT molecular dynamics, are also short to overcome nucleation barrier timescale. And indeed, what we see at different temperature and pressures that if you look carefully at your simulation, and you average over a window of 0 to 0.2 picosecond the position of the hydrogen, what you see is that they operate some fluctuation around the crystalline structure. Most importantly, this spurious solidification happens in what you are supposed to simulate a liquid, and happens very close to the putative first-order liquid-liquid transition predicted by a normal standard molecular dynamics method. So this casts some doubts about the validity itself of the existence of this first-order liquid-liquid transition, also because these points and this line lie very close to the melting line, which is anomalous, as I remember, so is re-entrant. So it's time to perform some systematic study and look on this system with a different method, different perspective. So what can we do more than that? We know that unfortunately there is this separation of size and time scale between first principle simulation and empirical models. So quantum Monte Carlo and DFT can tackle order of 100 electrons, and if you equip them with the molecular dynamics integrator, you can reach something like picosecond time scale. while empirical model can for sure look at tens of thousands particles for nanosecond, but you lose all the first principle accuracy, so you lose the chemistry. Now, since you remember the title of my talk, I will tell you that machine learning can be a tool to bridge these two worlds. And I will make use of all the nice introduction of the previous talk, skipping all the details and just give you the overview of the methods. So the setting is supervised machine learning. So as much as in a normal supervised machine learning task, you learn a mapping between an image and a number, a label, for example. Here, and we use the framework of Beller and Parinello that has been introduced several years ago. The machine learning is asking the machine, the artificial intelligence, to learn the mapping between a structure and its energy, effectively bypassing the need to solve the Schrödinger equation at each ionic iteration, in a sense. And if you plug a DFT type of dataset with PB, the neural network should learn exactly a PB description of the system. If you plug a different solver, the neural network should learn a higher level of the theory. So we use the N2P2 code, which is a tool to perform this kind of learning. We construct several generations of the machine learning potential. This is open source in the repository of Bin-Chin Cheng, who is the first name of the paper. She was a PhD student in Michele Ceriotti group, and now she's in Cambridge. So everything is available for your testing also. And so we perform this machine learning potential training. This can be then interfaced with LAMPs to run this large-scale simulation. We perform also benchmarks, of course, but in the interest of time, I will skip this part, although it's very important.
It's 5 minutes, more or less.
Yeah. Okay, thank you. And then let's jump to the result. So first, I say again, so now we have this machine learning potential that allows us to run 1,000 of atom simulation for 400 picosecond long simulation, and then we can scan the phase diagram with a much finer mesh compared to what is possible before. So here we plot the average order parameter, which is the molecular fraction, namely blue area means it is a molecular fluid or solid, while red area is atomic. So first we rediscover the reentrapment line of hydrogen. We also rediscover the candidate test crystalline structure for this system. Again, remember, without putting any human intervention in this, so just by cooling the liquid. And then we focus on the liquid-liquid transition, and we see that there is a lack of sharp transition between the blue and the red area. So this is already an indication that maybe there is not a clear phase-order transition, and we substantiate this claim running for the first time, some ab-initio thermodynamic model on this system. And since these simulations now are quite inexpensive, we can even run metadynamics to artificially enhance the molecular dissociation. So we can compare our simulation with a regular solution model, and where delta G is the chemical potential difference between the atomic and the molecular. So the molecular fraction is the order parameter. Omega is the non-ideal enthalpy of mixing. So we can run simulation, metadynamic simulation at different x, p, and t, obtained by fit delta G and omega. Now this is going a little bit technical, but just follow me. So after this, we fit again these trends only to get these two curves. So the coexistent lines, where is well delta G equals 0, which is the temperature at which the two fluids are equally stable, and the phase separation line, which is the temperature below which there is a phase separation between two liquids. So thanks to this machinery, we can draw this line in the phase diagram. And we see that the intersection is quite a low temperature and a high pressure, this orange star. So certainly it's not around 2000 Kelvin like it was predicted with normal ab-initio molecular dynamics. So if now we zoom a little bit more, we have 3 lines again. So one is very important, is the melting line, the purple, which has been rediscovered by the machine learning potential. Then there are these other 2 lines that meet at the critical point. The critical point is line really close to the melting line. And this allows us also to provide an explanation and reconcile the experiment, because if you assume now that the critical point is deep in the solid and there are this VDOM line that emanates from it, then given that the experimental setup trace different quantities, can be also understood or understandable that different quantities signals these discontinuities at different places in the phase diagram. And we see that they all nicely extrapolate to this critical point. A more methodological aspect is that if we wanted to perform the same kind of computational experiment with the normal and molecular dynamic DFT, we would have used several hundreds million of CPU years. Namely, it would be impossible. So this show you that this machine learning powered strategy can really enable us to do this kind of very fine and let's say accurate molecular computational study. So just to say that there have been related work published some week later. So one again on hydrogen with machine learning, and another study by Roberto Carr and Benedetti on a conceptually similar system, which is the study of a liquid-liquid transition, but in water, this time using the same concept. So now the outlook, so there are a lot of things that one can be done starting from here. So one can start looking at the solid, really scan more and better the phase diagram. You can add more elements, for example, hydrogen, helium. You can directly probe helium rain, maybe, or also put other element, carbon, or you can also improve the accuracy, because I believe that this kind of study holds a great opportunity for normal DFT or electronic structure solver, because they make this system, this method really inexpensive. So, for example, you can also use better or more accurate exchange correlation functional, or use quantum Monte Carlo. And we know that for hydrogen, while we believe that the results are qualitatively correct, because we also run different exchange correlation function, if you really want to have a quantitative understanding of the phase diagram, you really have to have the best electronic solver in the market to train your neural network with. And with this, I thank you for your attention, and I really want to thank all my collaborators, which are essential in this study. So from the planetary science side, Ravita Led and Ronald Redmer. From the machine learning side, which is the core of this talk, Bin-Chin Cheng, Chris Pickar, and Michele Ceriotti. And I want to talk as well Sandro Sorella, who was my PhD supervisor and that introduced me to the physics of hydrogen some years ago. So thank you very much, and I hope I've been in time, more or less.
Thank you very much, Guillermo. It was a very nice talk. It's nice to see what one can do now that these machine learning methods are out of their infancy. So we have a lot of questions and little time, as we are already far beyond the end of everything, but I think we can have a quick question, perhaps the one by Nathan Delman. Wait a minute. So Nathan, can you talk? And
can you hear me now?
Yes, we can hear you. Yes.
Okay. Thank you. Thank you very much, Guillermo, for the great talk and for showing how strong these neural network applications can be. So I just have two small questions. Firstly, considering that you're sampling in under such extreme conditions, it's always possible that the neural network can move outside of the region where it has been originally trained. Could you elaborate a little bit on the tests that you did to ensure that there is no extrapolation going on and that the model is robust?
Yeah, I mean, indeed, at the beginning, we train only with liquid structure. But it was nice that even by training on the liquid structure, we were able to see very well the re-enter melting line. So namely, already in the liquid, you can learn the interatomic environment of hydrogen. Then I'm going more into details on your question. Yes, we did several generations of this machine learning potential, including more configuration where it was needed. For example, along let's say the believed liquid-liquid transition line, and then we perform systematic tests also against let's say normal DFT simulation on sites which are possible to be explored. So yes, what you say is certainly true, and we take our precautions.
Okay, so you mean that you recalculated some of the predicted calculations then in DFT?
Yeah. So we were really able, for example, to start from a already published configuration and rediscover all the molecular dynamic RAM. So with the molecular with the machine learning potential, you can really see that the purple line falls exactly on the green line, which is a trajectory that we got from a previously published work. So this is like an amazing test, I would say.
That's nice. That seems very robust. Then my second question was that
sorry, Nathan, but I think we really have to interrupt you because we are really very far beyond any time allocated to this.
No, that's fine. Thank you very much.
So I'm sure you can get in contact with Guillermo and ask the question. And the same is true for all the other questions which have been around here. So thank you again very much for this talk and for all the talks we've had. It was a very nice session this afternoon. And yeah, and perhaps Nicola, I don't know how you want to.
Well, I think we deserve a 10-minute break, and then we can go to the Zoom rooms for the poster session. So I suggested we start in 10 minutes. So, and that will be more interactive. So I guess you have all the links in your emails you have received. So see you there, and see you tomorrow at the same time here for the second day of this workshop. So thank you very much, and see you around. Yes.
Goodbye, everyone.
Bye-bye.